Okay, so let's get started. Two talks today. This is our cosmology discussion that moves to Friday. And our first speaker is Hyunbae Park. He's just completed his PhD at University of Texas in Austin. He was working on small-scale structure of the intergalactic medium, doing some radiative feedback simulations, and also working on Apache reionization and detailed predictions using large simulations for the KSE. And now he's also working on KSE also at late time. And that's part of what he's going to tell us about today.
Thank you. Okay. So I'd like to first thank CITA for this opportunity for giving talk. So we'll have two KSE talks here, I guess. I was going to talk about something else, then I realized Emmanuel is going to talk about KSE, so I think it's a good idea also for me to talk about KSE. So SC effect is a term for the change of the temperature when the CMB photons get scattered by free electrons from ionized gas on the way from the last scattering surface to us. And then we basically want to learn about the baryon and on the way by looking at this signal. So there are two things happening when this scatter happens. So the first thing, the thermal SC effect, which is in general more generally known as the SC effect, is a distortion of the CMB blackbody happening when the energetic electrons kicks the low energy CMB photons to higher frequency. The kinetic SC effect, which I'm going to mainly talk about today, is a Doppler effect. So when the ionized gas scattering the CMB photons are moving toward or away from us, then the scattered CMB photons will be blue or red shifted accordingly, depending on the line of sight velocity. So here's the cartoon picture. If you think about the epochal reionization, then you have neutral IGEM embedding this ionized gas surrounding these galaxies emitting UV light. Then the H2 regions will have some line of sight motion. It could be moving away from us, moving toward you, or could be moving perpendicular without any line of sight velocity. Then the CMB will be red shifted or blue shifted, or it will remain the same depending on the line of sight velocity. So the change of temperature quantitatively is weighted by the optical depth of the free electrons. Of course, the more you scatter the photons, the stronger the effect should be. And it's weighted by the line of sight velocity because it's Doppler effect. The optical depth is it goes as the density of the ionized gas. So you basically pull out this constant like speed of light, hydrogen number density, and cross-section. Then you're left with this integral of what we call momentum field of ionized gas. Then the CMB fluctuation, the angular power spectrum from this kinetic SC effect is given by some constants and the line of sight integral of this what we call the transverse momentum power spectrum. So let me briefly introduce what we mean by this transverse mode. So if you think about a vector field, momentum field we talk about, and then you take out a random plane wave out of it and look at it, then it's got a direction of the vector itself and then the propagation direction, which do not necessarily be the same as each other. Then you can decompose this vector field into a component that the vector is parallel to the propagation direction and perpendicular to the propagation direction. For the parallel mode or longitudinal mode, if you just think about a line of sight, just random line of sight, and you think you are going through this direction, then you have negative dot product here, positive dot product there. You have this cancellation going on forever, so you never accumulate the signal. If you want to avoid the cancellation, then you want to take this line of sight. Then it's going to be perpendicular to the vector itself, and then you get no dot product. So to avoid that problem, you want to have a eventually you want to have the transverse mode in your integral. That now, if you take this line of sight, then the integral now can accumulate as you propagate through the line of sight. So that's why you have this the transverse momentum field here in this integral, the longitudinal mode gets wiped out as you do this line of sight integral. So then what we see from the observation, so currently the South Pole telescope is putting some constraint on this small scale high L mode of the CMB. There are three sources: foreground galaxies, thermal S effect, and kinetic S effect. They currently have some constraint on the kinetic S effect at L of 3000 or 7 arcminute, which is like 2.9 plus minus 1.3 microkelvin squared in terms of D of L. So a group like ours working on the simulation thermal reionization, we want to take this observational constraint and subtract the post-reionization contribution out of the total, and then we have observation constraints on the reionization signal. We basically want to predict reionization case signal with using our simulation and compare with this observation constraint. If it falls out of the observationally allowed range, then we basically rule out that model. That way we can constrain the reionization. In this talk, however, we'll talk more about our result of revisiting this post-reionization signal that all the reionization studies are just relying on, and we found something actually to be fixed about that. So I'll talk about that part today. So if you compare modeling the post-reionization and reionization contribution about this case signal, there are two different issues for each of these components. So for the reionization part, if you fix the angle, say 7 arcminute, L of 3000, then it's roughly like 15 megaparsec over h co-moving at ratio to 6 or above. Then their density and velocity field are in the linear regime. Recall that we want to model this ionized momentum field for this KS effect. Then this ionization field is going to be fluctuating in the large scale that we have to model them correctly to get this reionization signal. In the post-reionization regime, it's simpler in a sense that everything is ionized, so we can just say x equal 1 and take it out. But then this density and velocity fields are in the nonlinear regime because it's more evolved, it's lower redshift, and also we are looking at the smaller scale as we approach, as it gets closer to the observer. So let me briefly let me clarify why we want to revisit this post-reionization model. So in principle, to model this nonlinearity, we want to run simulations and then calculate the momentum power spectrum out of it to basically come up with this nonlinear momentum power spectrum. But in reality, I'll explain in a minute. For the reason I'll explain in a minute, this modeling momentum power spectrum requires a huge dynamic range. It has to have large box and then high resolution at the same time, which makes it quite expensive to actually run simulation for every different set of cosmological parameters. So people have been relying on analytical expressions for momentum power spectrum in the nonlinear regime that came from Hu 2000 or Mai and Fry 2002. And there were several works that tested the analytical expression against the simulation. But here we are sort of doing the same thing, but at the higher accuracy, I would say. So in the previous work, things were checked for accuracy of factor of 2 or an order of magnitude. We are now going to trying to make that as accurate as like 5%. So here is our Mbody simulation. We got 1 gigaparsec in the side, and we got like 1,000 grid and like 30 particles on average per pixel, basically trying to resolve everything down to 1 megaparsec. Now let me briefly tell you about the nonlinear model of this momentum power spectrum. So in the post-reionization regime, everything is ionized to a good approximation. So we can say this ionized momentum field is V times 1 plus delta. Then we have this first order term V and plus V delta, which is a product of these two terms. So it's the second order term. In the Fourier space, the second order term becomes a convolution, which actually is why we need to have this huge dynamic range, because this convolution is going to couple all the mode in the large scale and the small scale with other field in other mode in both in the small and large scale. So you want to have both the large scale and high resolution to include all that goes into this convolution, which is typically ranges from 1 gigaparsec to 1 megaparsec. Then if you take the transverse mode, there is negligible transverse mode in the velocity field, so you eventually have this second order term. In the power spectrum, basically you square that, and eventually you end up with this bracket of this fourth order moment, 2 density fields and 2 velocity fields. There are people who have been using this convenient relation that breaks this fourth order moment to 2 pairs of second order moment, and then you have 3 terms, basically 3 ways of pairing 4 terms into 2 pairs. Then these pairs become power spectrum that we can model easily. And then people have been basically coming up with analytical models for density and velocity power spectrum, and also velocity cross power spectrum to come up with this momentum power spectrum in the nonlinear regime. So just to show you the idea, so here I again have this CMB angular power spectrum given by this integral of the momentum power spectrum. So if you plot the integrand here, just to show you how much contribution comes from given redshift, and I'm comparing that for the nonlinear calculation, so P of Q with nonlinear power spectra and linear power spectra in the dotted line. You see a huge boost due to this nonlinear power spectrum preferentially in the lower redshift around between like 0.5 and 1.
Where does that reach? If you were plotting the cumulative one, where would it be at half?
So this area between this curve is directly proportional to total signal. So this is like half, I guess. So maybe 1.
Oh, okay.
Yeah.
It says per Coulombian distance on the vertical. That's why I was asking.
Yeah, and this everything is actually plotted linear in the Coulombic distance. So yeah, then we actually want to test this analytical expression. So since we have this giant Mbody simulation, we can directly calculate this momentum field and take power spectrum it. And also we can go ahead and take density and velocity, velocity, and density velocity cross power spectrum from the simulation and plug those into this integral, and then they're supposed to be agree. But the result said they didn't agree. So this is the ratio of this analytical expression evaluated with the power spectra from simulation and the actual momentum power spectrum. And they were off, depending on scales, from 10% to like 25%, which was quite puzzling to us. So we tried many things to actually explain this discrepancy, and we finally came back to this convenient expression that actually was valid only when the fields are Gaussian. So in the non-Gaussian regime, or in the nonlinear regime, the fields are non-Gaussian, and this is actually not going to hold precisely. There is going to be what is called the connected moment that will actually give extra contribution to the momentum power spectrum. Yes?
Is this using the nonlinear power spectra for delta and V in the unconnected terms when you make the plot?
I didn't show you the connected term yet, but you're talking about this plot here?
Yeah.
So yeah, all the power spectra came from the simulation. So here, first we directly calculate the nonlinear momentum power spectrum from the simulation. And also we did do that for density and density velocity cross power spectrum, and try plugging those into this integral. And if this expression is accurate, then those two results are supposed to agree with each other, right? And that's what we're doing, and we are finding this discrepancy here. So, so it was a little bit tricky because the non-Gaussianity cannot be expressed in terms of two-point correlation function or power spectrum. But we could do that up to some scale using the perturbation theory that we expect to work up to quasi-linear scales. So if using the perturbation theory, we can basically express the nonlinear contribution in terms of linear terms, and then the linear terms are Gaussian, and then we can hope to actually derive the connected term out of this perturbation theory expanded terms. So So in perturbation theory, we have this delta and velocity divergence expanded like this, first order, second order, and blah, blah, blah. And then, for example, we can take the second order term and express that in terms of two first order terms that are Gaussian. And we have these functions that Yashin showed us yesterday. But it's known, so we can actually go ahead and express everything in terms of these first order terms. So now we come back to this fourth order bracket and express that in terms of the velocity divergence that perturbation theory can handle. And then the next leading order is going to be in the sixth order, coming from either two second order terms and two first order terms, or one third order term and three first order terms. I'll show you how we do that for this term, for example. Basically, we expand these two second order terms in terms of first order terms. Then we have six first order terms. And then we can break this sixth order bracket into three pairs of second order brackets. And we have 15 terms like this in total. And these are the 15 terms. You don't have to read it. But then we want to actually take out the unconnected moment and separate out the connected moment. So we came back to this fourth order, four terms, and then do the unconnected term to just C. And then we in the end have these three terms that are subset of these 15 terms from this unconnected moment expression. Then, these rest 12 terms are from the connected moment that are not actually taken into account in the previous model. So you do that for all the other combinations, and you come up with the expression for the connected moment of the transverse momentum power spectrum to the next leading order. And you have a bunch of F's, G's, and P's. P is density power spectrum in the linear regime, which we all know. So we can, in principle, evaluate this expression to get this extra power. And we did that here. And now we account for the missing power up to like 0.3 in megaparsec, h over megaparsec, so which is expected. So we have extra power still not accounted for this by this next two leading order expression, but it's expected because higher order terms are going to be dominating here. So this sort of confirms that this missing power indeed came from this connected moment that was not counted in the previous model.
What do you call the connected part? It's you're assuming Gaussian, so ultimately everything is going to be equal to the product of the power structure. But so the way you call the connected part, you're deriving from like the higher order configurations.
Yes. So if you just go back to this original fourth order bracket, and then here you don't assume things are Gaussian. For example, the second order terms are not Gaussian, right? Then if you expand the second order terms into two first order terms, then they're going to be, each of the first order terms are Gaussian. So you have this sixth order moment. So the product of two first order terms are not Gaussian, but each of them are Gaussian, right? And that's how perturbation theory basically expands the nonlinear terms. So yeah, the actual kinetic SC effect comes from this highly nonlinear regime. So this is not going to be so useful there. But at least this tells us that we can trust this extra power we find in the simulation. So now we are back to this kinetic SC plot. And the next two leading order expression gives a tiny extra power in the KS signal. It's like 4% of the original. Then if you trust the extra power from the simulation, we have something like up to 10%. We are not sure about this low redshift power because we run out of resolution there, but that's the idea. Then we come back to this big picture about the KSC. So people originally have something like 2.0 microkelvin squared for the post-reionization KSC, but now from this unaccounted connected moment may increase 10% extra KS signal. Then maybe we will have less budget for the reionization KSC. So that's the summary. So we find the discrepancy in the nonlinear power spectrum model and the simulation. And using the perturbation theory, basically, we proved that that came from this connected term that rises in the nonlinear regime. And basically, that adds extra 10% power to the current model of the KSC signal. That's it. Thank you. 25 minutes.
I had a question. Oh, all three? Yeah.
Yeah,
Go
sure.
ahead.
So you thought about using a halo model approach, as a...
So people use, when they just take this analytical model, and then when they do it without simulation, they just take halo model for this nonlinear PDD, P delta.
Yeah, also for the other, you could kind of use halo model.
The halo model actually, so we in the end so you were talking about the connected term, right?
Well, the whole thing, I'm saying you can just do a halo model as opposed to this, 20th order extension that you're doing.
So we in the end want to have everything in terms of first order term if we want to do this, right? Do this analytical calculation, but halo model does not actually tell us about this higher order.
You can calculate all of the correlation functions in the halo model, let's say.
Oh yeah, that's.
So I'm wondering if you thought about, okay, but they're apparently not.
Yeah, I see what you mean, but I don't think it's possible to actually derive on this fourth order moment all the way down to I don't know.
Okay.
Yeah.
Wait a minute. So I want to go back to this point. I think it's pretty interesting. The halo model is a natural one in order to get the short distance K structure.
Yeah.
And I would expect that we'd be extremely surprised if the internal motions within a collapsed structure would be of great importance.
The velocity.
Essentially smoothing over them in any realistic experiment. So really, this is what was in effect called the it used to be called Kinetic Sunyaev-Zel effect. That was modeling things in terms of effective halos.
I see.
Were propagating at so many velocities. What we do with the patch is so for us, it would be absolutely straightforward to get the momentum field, and then what's left is the residual, and the residual is complex because you take that out, the portion. But nonetheless, I expect that would be a very good strategy to try and go after this.
Yeah, I guess.
And apart from everything else, it's really difficult.
Yeah, I guess. Yeah, I should think about it. Think about using the halo model actually to estimate this.
You have to for the high K. It's not just the velocities which do cancel, but it's the momentum, right? So there's a density profile.
Well, exactly.
So you care where the electrons are within the halo,
Yeah.
and that's really important for
Yeah.
structure.
Yeah.
Yeah, I don't know. I mean, it's true that, halo model, in fact, that we make a spherical approximations of all of those problems.
Yeah.
The proof on that there are all those problems, but nonetheless, in terms of capturing what would probably soak up a certain amount of what you're seeing in the that would be it. A good way to check that, I don't know if you've done it, a good way to check this is just take the simulation and start to do measurements with halos cut out. So you just sort of rank order the halos, and you see how the power, the momentum power is going as you progressively short out the higher mass objects. Now that would tell you the effect of those things on.
Yeah. See.
So is this, it's a little bit confusing because you have a simulation where you know the momentum field. So if you wanted to, which you do, you just calculate the power spectrum.
Yeah.
Which is the real thing. And then this only calculating these higher order terms only helps you in the quasi-linear regime, right?
That's right.
Okay. Everything else, you would have to model it using another way. Basically.
Exactly, yeah. We have everything in the simulation, but yeah, with this analytical calculation, we did only up to quasi-linear scale.
So, are there any more questions?